name is Ted Allard, and I'm sitting in front of what used to be the main gate of the Calaveras Cement Company plant near San Andreas. This plant was started construction in the spring of 1925. Construction was finished in 1926, and only a month later, the first shipment of rail went out of here for use in the valley. The plant was at one time the largest private sector employer in the county, and there were approximately 450 employees at one time, and in later years, after we became a little more automated, we were down to about 150, and the plant closed in the 1980s. It is now being demolished, and the liability hazards taken away for the company. Calaveras Cement Company's associated companies are still doing well, and we're still making cement in Tehachapi and in Redding and in British Columbia. So the company is alive and well. Please enjoy the two films that are coming up. One was filmed in the 1940s, and after considerable expansion and automation, the second one was done in the 1950s. And if you will watch the film, for you old-timers, you'll probably see a number of familiar faces in some, particularly the second film. Thank you.
As far back as there is any recorded history, man has felt the need of a cementing material. The early Egyptians, in building the pyramids, used a mortar which modern analysis shows was an impure form of plaster of Paris. The Romans combined lime and volcanic ash to make cements that in some places have endured until today. Lime mixed with sand has long been known as a cementing material, but it has one great disadvantage. It will not set underwater. In the middle of the 18th century, an English engineer, John Smeaton, discovered that if limestone containing clay was burned and then pulverized, it would harden underwater. Portland cement was born, but it was 100 years before the child grew up. In California, always thought of as the gold mining state, the young enterprise has reached full maturity. Last year, the state's cement industry produced $80 million worth of cement, compared with $9 million worth of gold. In California's Mother Lode in Calaveras County near San Andreas, nature has been kind to the cement industry. Here are found not only pure limestone in great quantity, but also many varieties of silicate rocks. These can be blended with limestone to make Portland cement that will meet any specification. Here, the Calaveras Cement Company has its plant. And here in the rich foothills of the Sierra, we begin the story of modern cement. The first step in the production of Portland cement is the mining of the raw materials. Each day along this road, trucks roll out to the quarry where the elements of cement are found. But before raw material can be mined, it must be located. The quarry contains many millions of tons of limestone. Here is some of the equipment needed to break it. This is a diamond drill, which can bore deep into the rock and pull out a little cylinder or analysis. Here, the drill is pulling core, and the sample thus obtained will tell the miners what lies below the surface. This is a blast hole drill, somewhat like a large diamond drill. It bores holes from 6 to 9 inches in diameter in the rock to be broken. The men are now lowering explosive into a hole. It takes about 1/3 of a pound to break a ton of rock. As much as 500,000 tons have sometimes been broken in one blast. The holes are covered with finely cut limestone left over from drilling. And now they are ready to be connected together with detonating fuse. PETN is used for this purpose. It burns or explodes at a rate of 20,000 feet per second and detonates the explosive in the holes. At this point, the loaded area is cleared of all but 2 men, and a cap is placed on the end of the fuse before connecting it with an electrical blasting machine. This cannot be done until the last minute because of the danger of premature explosion. Blasts can be set off by static, so proper precautions must be taken. All is in readiness. The man approaches the electric magneto, which actually sets off the blast. He lifts the plunger. He pushes it down. The smoke rolls away over a jumble of scattered stone. However, much of the rock broken by this primary blast is too large to go into the plant's crushers, and one of 2 methods may be used in breaking it down to a suitable size. Block holing, seen here, involves drilling 1 or 2 holes in each boulder, packing in explosive and blasting. The other method, which is coming into more general use, is known as drop ball. The drop ball can be used all day alongside the shovels and drilling machines. But block holing, like the primary blast, requires that men and equipment be cleared out of range before the shot is fired. Now the rock is broken to size and ready for its journey to the plant. The electric shovels go into action. A side dump truck, which holds 35 tons, backs up to the shovel, whose dipper scoops up 5 yards of rock each bite. The smaller end dump truck, seen here, has a 25-ton capacity, but it is faster and more mobile than the double units. These silicate rocks must be mined for blending with the limestone, or simply to remove them from limestone which is underneath. Trucks must have access to any part of the quarry, and so road building goes on continually. The bulldozer, or D8 Cat, is almost universally used for this purpose. Out of the quarry comes the truck. Its load of rock has been blasted from the earth and then broken still smaller by block holing or drop ball. Now it must go through the various plant processes. First in line is the primary crusher building, where we see an end dump truck unloading into the crusher. This side dump truck is dumping into the opposite side of the crusher. The crusher is a huge machine which breaks the rock into pieces approximately 4.5 inches thick. Each process breaks the original rock into finer and finer bits. Now it is swiftly on its way, carried up by covered conveyor belt to the secondary crushers. The belt discharges its cargo into surge bins, which feed the crushers uniformly. These are reciprocating feeders, pushing the rock out of the bins. When the secondary crushers have finished their job, the rock is broken into 1-inch pieces. Next stop along the road to finished cement is what is known as raw storage. Here the massive crane is at work, picking up rock which is mixed and blended as necessary and dumped into raw bins. The rock now flows by automatic feeders into the raw mills and classifiers. The finely ground rock and water, known as slurry, pours over the lip of the bowl classifier. At this point, the slurry contains 85% water and 15% ground rock. Since this is far too watery to feed into a kiln, the mixture is first sent into thickeners. In these 150-foot diameter tanks, the solid material settles. The mixture is then circulated by pumps until the slurry that comes out is 65% solids and 35% water. For blending, it goes to these silos, each holding from 1 to 2,000 barrels. Here it is kept agitated by air to ensure uniformity of composition. The blending process continues until slurry of exactly the desired type is obtained. Now the mixture is ready for the kilns. 2 of these tubes are 240 feet long, and 2 others are 360 feet long. They slope 1/2 inch per foot and make 1 complete revolution each minute. Their combined production is 10,000 barrels a day. The slurry is fed in at the high end and flows slowly down toward the fire, taking some 2 hours to make the trip. At the firing end of the kiln, the final step of the burning process takes place. Here we see clinker being formed at a temperature of about 2,800 degrees Fahrenheit. The exhaust gases from the kiln go out through a 200-foot stack. Dust is removed from these gases in a Cottrell electrical precipitator, which employs 60,000 volts of direct current electricity. The dust falls to the bottom of the Cottrell and is fed back to the kiln. All kiln operations are controlled by complex recording instruments. Temperatures, drafts, kiln rotations, and speeds are recorded. In fact, everything that goes on during a burning shift is noted here. Next morning, the reports go to the chief chemist's office so that any deviation from normal procedure may be observed. The rock which we saw blasted from the quarry has been transformed into this clinker pile. However, it is not yet cement. A big crane moves it along to the finished grinding mills, where it'll be ground with about 3% gypsum. Without that portion of gypsum, which serves to regulate the set, Portland cement would be unusable. At the finish mill, the clinker is first broken down coarsely in the preliminator. Then long tube mills reduce the clinker to a very fine powder. The temperature of the cement must be controlled during grinding, so the mills are sprayed with water. When the water itself becomes too hot, it is cooled in this tower so it can be used again. The product of the finish mills, which we can now call cement, is transferred across the bridge to the finish silos. There are 12 of these, holding in all 180,000 barrels of cement. We are looking at the silos through the flowers of Kentucky House. Lawns and gardens make a pleasant setting for this comfortable building, maintained as a guest house for company visitors. Kentucky House was originally a roadhouse for the stages of 49 and is famous throughout the Mother Lode for its good food and its beautiful flowers. The gardens extend almost to the foot of the silos which contain finished cement, although it is not yet ready for shipment. Before leaving the plant, the cement must pass a rigid series of tests, both chemical and physical. Here, a sample is being weighed for chemical analysis. This is a small electric muffle furnace, in which precipitates may be burned off or where fusions of raw materials are sometimes made. The crucibles are usually left in the furnace from 30 minutes to an hour. The product is then ready for further analysis. This is a titration. The solution in the beaker is being tested for the total amount of lime, a critical part of cement. Potassium permanganate, a deep purple solution, flows into the beaker from the tube or burette above. As long as the solution turns white when stirred, an insufficient amount of liquid has been added from the burette. When a slight purple tint remains, the analyst can read the amount used on the burette, and it will tell him directly how much lime the solution contains. Cement must also be tested for flowing or plasticity. On the flow table here, a mixture is made of certain definite amounts of cement, sand, and water. The table is then jarred a given number of times, making the cement spread. The size to which it spreads is a measure of plasticity. In this physical test, a cube of cement is compressed by a plunger. The needle indicates the pressure required to break it. In a similar test, the jaws of this machine are placing tension on a cement briquette. When the briquette breaks, the needle on the dial will drop back, and the dial reading at that point will indicate the pull or tension required to break the briquette. Only after the cement has passed these and many other tests is it ready for shipment. In the pack house, the bags are automatically weighed as they are filled until they hold 94 pounds net of cement. The full bags are moved by means of a conveyor belt underneath the packing machine. After being stacked on hand trucks, they are wheeled out to trucks or railroad cars for shipment. Customers sometimes send their own trucks to pick up an order. Here is a load being tarped down to protect it from moisture. There was a time when shipping cement by the sack was the only method used. In recent years, however, there is an increasing trend toward bulk shipment. These bulk trucks hold about 115 barrels per load. The whole loading process is handled almost entirely by machine, thus saving the cost of bag packing. This is one of the most modern of the bulk trucks. It is capable of carrying 120 barrels. It is filled by machine, weighed on big scales, and made ready for the highway. And so the product leaves the plant which transformed it from rock to cement and heads into its final phase, a building material. Reaching its destination, the truck will unload mechanically by dumping into a bin under the roadway. The cement is raised on the elevator into the bins at the top, then it drops by gravity into batching equipment. Every ingredient is weighed: cement, sand, water, gravel. The product is then ready to go into the mix truck and be carried to the buyer. It may be destined for use in the construction of a private home. Or perhaps it will line the banks of an irrigation canal, benefiting thousands. For modern cement is a product of machinery, and its superior quality remains within the budget of all. Out of John Smeaton's discovery has grown the finest building material ever developed by man. Much of our present civilization rests literally on cement foundations. Great dams for irrigation, power development, and flood control. Highways for the modern automobile. Bridges to span our rivers and harbors. The mighty buildings of industry. And homes for the millions. This is only the beginning of the wealth created by cement. Other material must be combined with it. Labor must be hired to place it. The homes and stores and factories which are built on cement mean prosperity for all.
Story of Portland cement, a product that has played a key role in building the West, and one that continues to contribute to growth and progress everywhere. One of the initial steps in the making of cement has taken place. 100,000 tons of limestone has been broken. Thus, nature has given up the raw materials. Limestone and siliceous rocks, after complex processing, will become Portland cement. And what better setting for our story than the mother lode country of California? Before blasting began, sample cores were tested and the section to be mined was chosen. The drilling of the blast hole gets underway. A rotary head that turns the drill is mounted on tracks at the top of the shaft. This is lowered until the rock bit is ready to drill. The drilling of the 10-inch diameter hole begins. When completed, this hole will be 55 feet deep. When 40 or 50 holes have been drilled, the explosives are lowered into them. The explosives are then covered with limestone chips recovered from the drilling of the holes. With all holes charged with explosive, tamped and wired together, the blasting signal is given and the quarry is cleared of all personnel and equipment. The powder man carries the blasting machine to a blast shelter. He connects the wires which detonate the explosive. He depresses the charging switch. As the charge builds up, the needle swings over until it is in the firing zone. He presses the firing switch. From the air, a more comprehensive idea of the layout of a cement rock quarry may be obtained. Years of blasting and mining rock have carved this enormous hole in the earth, cutting deeper and deeper ledges. Called benches by the miners, these ledges average 50 feet in height. They serve as work areas for further drilling, blasting, and recovery of rock, and also as roadways for transporting rock to the plant. As soon as safety permits, men and equipment move into the blast area. D8 cats scrape the rock into piles for loading and clear the way for other equipment. Much of the blasted rock is still too large to be handled by the crusher and must be broken still smaller before going to the plant. One method of accomplishing this is called drop ball. A 3-ton steel ball suspended from a movable crane is a most efficient boulder breaker in the hands of an expert operator. If the bottom of the blasted ledge, the toe of the bench, does not break clean, air drills are used to bore small holes into the rock. A few sticks of explosive are tamped into each hole in order to complete the blasting. When the rock has been reduced to a size that can be handled by the primary crusher, it is scooped up by electric shovels and loaded into 25-ton trucks. This load of rock is now on its way to the cement plant. The setting for the next phase of cement making is quite different. It is a highly complicated industrial plant requiring the services of hundreds of skilled workers. The nerve center of the entire operation is this administration building, which houses the planners, the engineers, the administrative heads of departments, and the laboratory. This new shop building, a fine example of a well-designed concrete structure, houses a large crew of highly trained men. They are kept busy on repair and maintenance of machinery and equipment. And this is the primary crusher, where the truckloads of rock are received. This crusher is known as a 42-inch gyratory, which breaks all rock received to 6 inches or less. The rock from the primary crusher is still much too large for the grinding mills, so a conveyor belt carries it to 3 secondary crushers. These are high-speed gyratories which crush the rock to 2 inches or less. Some of the rock is still not small enough, so a tertiary crusher is used to break the larger pieces to 1/2 inch. This product is then transported by endless belts from the crushers to the raw storage area, where it is piled according to grade. The grade of the rock has been determined in the laboratory by the testing of samples taken earlier. The operator of the overhead traveling crane picks rock from different piles according to the blend of limestone and silicates required and dumps it into the feed bins above the raw mills. From these bins, the rock is fed into ball mills where it is pulverized by steel balls. Water is added, and the resultant mud, or slurry, goes to the classifier, where the coarser particles are separated and returned to the ball mills for further grinding. The slurry is now 35% rock and 65% water. This is too much water for the kilns, so the mix is sent to thickeners, where the solids settle and excess water runs off the top. Now the slurry is 65% rock and 35% water. It is pumped to blending silos, where it is agitated by compressed air. Slurries of different chemical compositions are combined for different types of cement. The slurry is pumped from the blending silos to the kiln feed tanks and is agitated until fed into the kilns. At this plant there are 5 kilns, long steel cylinders lined with fire brick and mounted on massive tires. Those in the foreground are 360 feet long and 11 feet 3 inches in diameter and make 1 revolution per minute. The slurry is fed into the kiln at the high end and travels slowly toward the fire at the low end. At first, the water is driven off. Then, as the mix becomes hotter, the limestone portion is calcined. That is, carbon dioxide is driven off and quicklime is formed. At the firing end of the kiln, where the temperature is 2,800 degrees Fahrenheit, more than enough to melt steel, the quicklime and silicates combine to form cement clinker. The control rooms, with their many dials and recording instruments, show the progress of the mix in each kiln. Essential information is recorded, such as the temperature of various parts of the kiln and the chemical composition of the gases given off. This is the Cottrell precipitator. It removes dust from the gases before discharging them through the 200-foot stack. After the cement clinker is formed, it is dropped onto a traveling grate through which air is blown. The cool clinker is carried by a vibrating conveyor to the clinker storage area. An overhead crane fills its bucket and dumps the clinker into feed bins above the finish mills. This is cement clinker. Next, the clinker goes into the finish mills, which are similar to the raw mills. Here, with the addition of 3 to 4% gypsum, it is ground as fine as flour by the action of the tumbling steel balls. This is cement, produced at this plant at the rate of 4.5 million barrels a year. It is pumped from the finish mills to one of 20 storage silos, holding a combined total of 400,000 barrels of cement. Uniformity and quality control is of paramount importance in the production of cement and is the primary concern of the laboratory. Technicians are constantly analyzing samples taken at every step in the making of cement. Here, an analyst weighs a small sample preparatory to running a test. As all raw materials will not dissolve in acids, some of them must be fused to become soluble. This crucible, containing a weighed sample mixed with fluxes, is placed in the furnace. The contents are melted, thus combining and forming compounds that are soluble in acids. Now we are able to perform the necessary analyses. The solution thus obtained is analyzed for lime by dripping potassium permanganate solution into it. This is known as titration. The clear solution in the beaker is placed under a graduated burette filled with the reagent. The analyst drops the reagent into the clear solution until the color no longer disappears by stirring. When a faint purple tinge remains in the formerly clear solution, the analyst reads the amount used from the burette. This gives him the amount of lime in the solution. In preparation for compressive testing, this mixture of cement, sand, and water is being measured for consistency on a flow table. A mold is filled with the mixture. The mold is removed and the table jarred exactly 25 times in 15 seconds. The spread is measured to determine the consistency of the mix. All samples must have the same flow to give comparative results in the compression machines. Cement mixed with rock, sand, and water, concrete, is molded in a cylinder and cured under standard conditions of temperature and humidity. It is here being tested in a compression machine. With the cylinder in position, the machine is turned on and pressure gradually applied. 2 needles rise slowly as the pressure increases. When one needle drops, the cylinder has cracked. The other needle remains at the higher point, 57,000 pounds in this case, which is the compressive strength of the cylinder. When the cement has finally been tested chemically and physically and has met all specifications, it may be shipped. Today, 85% of the cement from most mills is shipped in bulk. The capacity of this modern bulk truck is 140 barrels. It is loaded and emptied mechanically, thus eliminating costly handling and considerably reducing the price of the cement. Cement is also packed in sacks, which the operator slides onto nozzles. Each sack has been completely sealed except for a small opening just large enough to receive the nozzle. After it is in place, a button is pressed and cement is blown in. The scale shuts off the flow of cement automatically when the 94-pound mark is reached. The sack is then dropped by the operator onto a belt that carries it to the loading platform where it is loaded onto trucks or rail cars. The making of Portland cement is a fascinating story. A story of almost automatic processing of rock by machinery into a gray powder, which, when mixed with sand, gravel, and water, becomes one of the strongest and most enduring building materials known to man. And the marvel of it all is the economy of cement, available for less than a penny a pound. But this is not the whole story. For cement is also the story of human endeavor and people. From the original discovery of how to make Portland cement down to the vast industry of today, it is the story of men who make possible the smooth and efficient operation of this complex process. Take Tormey Ward, for instance, checking out a truck. He has no trouble locating a good stream after work. Dave Cosgrave, draftsman, who is talking with Grant Metzger, plant manager, has a small ranch in the beautiful Mother Lode. Dante Chirolo, president of the local union, checks a fire hydrant on the job, returns home and relaxes in his lath house, known for its beautiful flowers. Norman Beebe, an analyst in the laboratory, shows a result to Bill Durland, assistant chief chemist. Here, Norman does some very practical work with cement in his backyard. At the guardhouse, we see Bob Layton and Molly Swinga, laboratory analysts who have grown beards for the annual Jumping Frog contest. They are well versed in the history of the Mother Lode and take pride in showing visitors the many reminders of the past. Reminders like the 100-year-old Kentucky House, originally a stagecoach stop, and now a unique guest house for plant visitors. The old Mark Twain cabin is an example of the rich historical background of this colorful territory. By way of contrast, a modern-day structure with its name a heritage of the past, the Mark Twain Hospital. But the widespread use of Portland cement has produced monuments to its utility everywhere. Here, for instance, is an example of the ease of handling cement in the construction of the Poe Dam in the Feather River Powerland. Nature is once again tapped for her resources through the medium of cement. Concrete-lined canals, such as the Delta Mendota, carry water hundreds of miles to the rich agricultural areas of California. And here we see its application in this residential area, with its attractive homes, sidewalks, and curbing. Contributing to the of our young people, cement goes into the construction of buildings like this modern school, a safe and functional atmosphere for learning. Today, the development of prefabrication in construction has resulted in even wider and more economical applications of the product. Factories rise from the ground in a matter of days instead of weeks or months, built upon Portland cement foundations and assembled with Portland cement floors, walls, and even ceilings. Factories, hospitals, and countless other buildings add to the beauty and prosperity of our land. Highway construction depends upon the use of cement in building today's high-speed freeways, approaches, and traffic exchanges. The nation's transportation ways demand an economical and durable material that will hold up under the rigors of constant use and in all kinds of weather. Portland cement meets these requirements. Our national defense depends upon cement too, illustrated here in this Army Nike installation. All around us, in the country and in the city, this unique building material is serving man. Portland cement is contributing in a very real sense to the continuing growth and prosperity of the West and the nation.